Hi, my name is Sarah Hankins, and I have my bachelor's degree in mechanical engineering from the University of Wyoming, and I'm currently working on my master's degree in mechanical engineering, also from the University of Wyoming. I like to start things off with a quote, so my quote for today is, "Obstacles are what you see when you take your eyes off your goal," by Jim L. So today we are going to be talking about finite element analysis, and in particular we're going to be talking about three linear elements in 2 dimensions. So this is a problem that we are going to be looking at. We are given a partial differential equation, which is the negative second partial derivative of u with respect to x equals f of x, and in this case f of x is equal to x, and x goes from 0 to 2. You're also given some initial and boundary conditions. Our initial condition is that u of 0 equals 0, so what this tells us is u's are our displacements, so the displacement at x equals 0 is equal to 0. And then we are given a boundary condition, which is a partial derivative of u with respect to x at x equals 2 is equal to 20. So this tells us that at x equals 2, there is a force of 20 at that point. So the first step in the process is to draw the picture. So we are told that we have 3 linear elements in 2 dimensions. So since we're only in 2 dimensions, we're just going to be dealing with a straight line. We have 3 linear elements, which means that each element is only going to have 2 nodes. We're also told that x goes from 0 to 2, and that each element is spaced equally between 0 and 2. So element 1 goes from 0 to 2/3, element 2 goes from 2/3 to 4/3, and element 3 goes from 4/3 to 2. Now at each of those 4 nodes, we're also going to have some variables for displacement. So u0 is our displacement at this first node, u1 is this displacement at second node, u2 is the displacement at third node, and u3 is the displacement at the 4th node. Now the next step in the process is to derive or write the functions for each of the elements. So we are going to start with element 1. We are going to begin by using that first equation, which is ue1 star of z equals c1 plus c2z, and we are using this because this is the function for linear elements. And then what we're going to do is we know that element 1 goes from 0 to 2/3, so we are going to plug in z equal to 0 and z equal to 2/3 into that equation, which leaves us with these 2 equations here. We have 2 equations, 2 unknowns, because we don't know what c1 and c2 are. Therefore, we are going to use these 2 equations in order to solve for c1 and c2, and you'll notice that they're going to be in terms of our displacements, because at z equals 0, we have a displacement of u0, and at z equals 2/3, we have a displacement of u1. So if you solve for c1 and c2, you'll get that c1 equals u0, c2 equals u1 minus u0 times 2/3. You'll then plug that back into the very first equation, and you get this equation down here. And then what we need to do is we need to separate out the u's, and once we do this, we will end up with our interpolation function. So once you separate the u's, you get this equation in the green box, and again, each term in parentheses are our interpolation functions for element 1. Since there are 2 nodes for each element, since they're linear elements, we are going to have 2 interpolation functions. So this is our first one for element 1, this is our second interpolation function for element 1. Again, we're going to do the same thing for element 2. We are going to use that same function for the linear element, so ue2 star of z equals c3 plus c4z. Again, same thing, so element 2 this time goes from 2/3 to 4/3. So we're going to plug that into that equation, set it equal to our displacement at u1 and our displacement at u2, because 2/3 is at u1, 4/3 is at u2. Again, we have 2 equations and 2 unknowns. You're going to solve all those out, separate the u's, and then you end up with this equation in the green box. And once again, those terms in the parentheses are our unique interpolation functions for element 2. Then you'll do the same thing for element 3, and this is the equation that you should get. Again, the terms in parentheses are the interpolation functions for element 3. The next step in the process is we need to determine the interpolation function matrix, the B matrix, the element stiffness matrix, and the F element stiffness matrix, and we're going to begin by looking at element 1. So first we're going to start by writing out our interpolation function matrix, which you can see right here. Remember, we get these interpolation functions from this equation. So we are simply taking the interpolation functions, which are inside the brackets, and we are turning them into matrix form. Next, you want to get your B matrix, and to do this, you take the partial derivative of your interpolation function matrix with respect to z. And if you do that, you end up with this matrix. And then next we need to determine the element stiffness matrix for element 1. And so to do that, we use this equation, which is the integral of B transpose times B. Remember, we solved for our B matrix up here. And if you plug that in, this is B transpose, this is B, and our integral goes from 0 to 2/3, because again, element 1 goes from 0 to 2/3. So if you multiply everything out, take the integral, you end up with this matrix, and then finally with this matrix. And then that last thing that you're going to do, you're going to solve for the F matrix for element 1. And to do this, it's the integral of the interpolation function matrix times f of x. Remember, in our problem statement, we were told that f of x is equal to x. So if you plug those things in, again, the integral goes from 0 to 2/3 because that's the coordinates for element 1. And in 2 dimensions, x is equal to z, so we can simply replace the z's with x's, and we end up now with this integral, so the integral from 0 to 2/3 of this matrix here. And then once you take the integral, you end up with your final F matrix for element 1. You're going to do the same thing again for element 2. So you're going to get your interpolation function matrix for element 2. Again, remember that comes from our equations. You're going to get the B matrix by taking the partial derivative of that interpolation function matrix with respect to Z. Then we want to solve for our element stiffness matrix K. For element 2, we're doing the same thing. So the integral of the B transpose times the B. If you do that whole process, you'll get this matrix. So this is the stiffness matrix for element 2. And then finally, we want to get the F matrix for element 2. Again, the whole same scenario, the integral of your interpolation function matrix for element 2 times f of x, which again in our case is x. Remember, x is equal to z in 2 dimensions, so we can simply put this x into the matrix inside, and then take the integral, and we end up with our f matrix for element 2. Again, you're going to do the same thing for element 3, and this is what you should have for the interpolation function matrix, for your B matrix, for your element stiffness matrix, and for your F matrix. Again, this is all for element 3. Fourth step is we want to merge our element stiffness matrices and our F matrices for each element into a global matrix. And so in order to do this, we are going to look at the element form and we are going to merge it into the global form. So this is the element form of our stiffness matrix for each element. So element 1, element 2, and element 3. And so these take the form of K11 at element 1, K12 at element 1, K12 at element 1, and K22 at element 1. You do the same thing, same format for element 2, so the only difference is our superscript is a 2. And the same thing for element 3, except our superscript in this case is a 3. So we are going to then merge these 3 matrices into a global matrix. And so you'll notice this right here is our element 1 stiffness matrix. This right here is our element 2 stiffness matrix, and this right here is our element 3 stiffness matrix. You'll notice that we had to merge or add together some of the components of the element stiffness matrices, and this is because element 1 and element 2 share a node, so that's why you have to add those two together, and element 2 and element 3 share a node, which is why you have to add these together. Once you form that global stiffness matrix, add all those components together, this should be the global matrix that you end up with. Again, we are going to do the same thing for the F matrices for each element. So in this case, these were our F matrices for each element, and this is the form that they take. So element 1 is F0 at 1, F1 at 1. Element 2 is F1 at 2, F2 at 2. And element 3 is F2 at 3. And F3 at 3. Again, we're going to put these into a global matrix, which should look something like this. Remember, again, element 1 and element 2 share a node, which is why we're adding these two components together. Element 2 and element 3 share a node, which is why we're adding these two together. If you add everything together, this right here is your final global F matrix. Next, we are going to plug these into our overall equation. So what our overall equation is our global stiffness matrix K times our U matrix, which again are our displacements at each of the nodes, equal to F plus Q. And so in this case, Q is our forces. And so if you plug everything in, this again is our global stiffness matrix. This is our displacements at each of the 4 nodes. This is the global F matrix that we calculated. And the last thing that we need to get is we need to get this Q matrix. So the 5th step is to apply boundary conditions. Remember, we were told that U of 0 equals 0. So at x is 0, it equals 0. Therefore, our displacement is equal to 0 at U naught. So this end is being held fixed. Then we were told that U prime at 2, so U prime at x equals 2 is equal to 20. So this means that there's a force of 20 over here at x equals 2. But remember, forces need to be equal and opposite, so some of the forces have to be equal to 0. Therefore, we must have a negative 20 force over here at x equal to 0. So then what we're going to do is, since we know that our displacement at U naught is equal to 0, we are going to set the first row and the first column equal to 0, except we're going to keep that diagonal entry the same. And then we are also going to set U naught equal to 0 over here in our displacement matrix. And then for the Q's, we know that Q3 at 3 is equal to 20, so we fill that in here. We also know that Q naught at 1 is negative 20, so we fill it in here. The other ones are zeros. And now everything is filled in the way we need it to be. So the 6th step and the final step in the process is to solve for our U's, or our displacements. So we're going to rearrange the equation. Again, these are the displacements we want to solve for. We invert our global stiffness matrix and then multiply it by the F plus the Q matrix added together. So that's why you have the negative 20 and the plus 20. And if you do this, you end up with, again, remember, U naught is equal to 0, U1 is equal to 14.6, U2 is equal to 28.9, and U3 is equal to 42.7. Remember, again, this just tells us how much each of the nodes are displaced. So that's how you do finite element analysis for 3 linear elements in 2 dimensions.